Here we are. So it's yesterday was 2 Minute Tuesday. Today is Helpful Hints Hump Day, the midday in the week. I've just got these silly names for each day of these events, but today, as I advertised, the focus will be very much on designing a battery storage system. And I'm going to do initially for off-grid this design, and we'll just basically draw some pictures explaining the requirements for overcurrent protection, isolation, etc., and referring back to the relevant standard, which is this one, AS/NZS 5139. Now, I've mentioned it a few times to people in these live streams this week, but I just should point out that this is now mandatory in Australia. So it's been referenced in AS 3000 since the beginning of the year. It came with varying levels of adoption, but basically 6 months is up in all states now, so that means it's in force. This standard is replacing AS 4086. So it's a new standard. It is quite comprehensive and it needs some explaining. So I've done a few webinars and few YouTubes on it so far, and I'll be doing some more. I should point out that you can purchase this from SI Global. This is not a sponsored event at all, but as a designer of systems and sometimes installer, I do need to have a copy of it. Reaching out to those in New Zealand, because we have quite a few followers from New Zealand on my channel. In New Zealand, this is a kind of a vague adoption because it's not yet referenced in New Zealand electricity regs. It is really a best practice guide, but it has been pointed out to me by the New Zealand regulator that since it isn't replacing an existing standard and that it is providing safety information, there is an argument that you do need to comply with it. So take that for what it's worth. It is actually a really good design document too, but there's some parts of it are a bit curly and a bit tricky. So today, because this is a live stream, you can chat to me, and yeah, I forgot I got my glasses on. I've got to take those off. That's my chilling out before the bright lights. So you've got these bright lights here before we start. So yeah, thanks Abby for reminding me. And yeah, just throw into the comments any questions or comments that you've got as we go, and I may answer some of those live. But I'm always tripped up by a technical question that I have to look up the answer to. So if there's anything that's a little bit I can't just give a straightforward answer to, I may just make a note of that and bring it into the next live stream. So I'll be doing another one of these tomorrow and the day after. So basically 3 o'clock Australian Eastern Standard Time, I'm doing these live streams talking about solar and battery systems. Okay, so let's get into it. I thought I'd start off with an off-grid system design just to sort of keep it traditional, because solar and battery used to really mostly focus on off-grid, and look at the implications of the new standard in terms of the design of an off-grid system, covering things like arc flash, overcurrent protection, isolation, location of devices, etc. So let me just flick over to my drawing pad over here. Okay. So this is I'm going to design a fairly chunky off-grid system. So it's a 48 volt battery. We've got 2 strings of 1500 amp hour sealed lead acid batteries. So that's a fair whack of energy stored in 2 strings, so times 2. And I'm just going to draw it in simple electrical symbols, how this might be considered. So this is a symbol for a cell. And we've got multiple cells, and there we go. So that is 1 string of 48 volts, which is made up of course, 24 2-volt cells. Okay, and that's a traditional 48 volt system. Now, if you're going to do a bigger system with 2 strings, I'll draw another one here. This. So there's our 2 strings of sealed lead acid batteries. We're going to connect it to some power conditioning equipment, which is a technical term for an inverter, because we're going to supply the customer with some power. So I'll draw an inverter over here. And in case there's any electrical engineers out there, I know there's at least one because I can see you, Abby. The symbol for an inverter is thus Appendix J of ASNZS 3000. It's not a connection diagram. You don't have to connect the DC to that side and the AC to this side. So just ignore where the lines connect. It's just a symbol for a device that converts DC to AC. So it's a conversion device. Now, we're going to need some isolation on this system. So at the inverter, so we're going to need to be able to isolate this system here. Now here's the first change from the old standard. You used to be able to put in separate overcurrent protection and isolation devices, but actually now you have to have them gang together. So you can't have separate fuse on the positive and a fuse on the negative, for instance. So here we've got a ganged combined overcurrent and isolation device. Typically, once upon a time, it would have been an HRC fuse switch, but I think that's getting to be problematic these days because the requirement is that if it's indoor, it needs to be IP23 for that's indoor, and if it's outdoor, IP56. And because most off-grid inverters generally are indoor products, so it's probably going to be the IP. 20. It's supposed to be 23. IP23, sorry. Don't know where 28 came from. Don't try and talk and write at the same time. So that's this device here. Now, IP23 is hard to achieve with an HRC fuse switch. You should check with the manufacturer if it is actually IP23. So you may need to choose another product, or as many installers are doing these days, using a suitably rated circuit breaker, because you can get some very high current DC circuit breakers for use in battery systems. The other thing that's changed too is we used to be able to connect those two strings of batteries in parallel straight to the inverter, but that's not the case anymore. And the reason for that is a very good one, which is that when you have a fault in one string of batteries, it can source current to the other string of batteries, or vice versa, and therefore you can have a very, very high short circuit current within a battery bank, and nothing's going to stop it except the thickness of the cable, so likely a fire. So the requirement now is where there are more than one string of cells connected in parallel, you need to have overcurrent protection. So you could have a fuse, you could use a device such as a circuit breaker, but anything that provides overcurrent protection. So there we go. So there's our string overcurrent protection. Only has to be on one pole, doesn't have to be on both. Now we could connect those straight to the inverter, but one of the considerations is distance. How far from the battery system is the PCE? Now I'll kind of indicate what the battery system is. So the battery system here is this area here. This is a box that the battery system's sitting in, and it's got some terminals on the outside. Now, if the distance between the PCE and the battery system, if this is greater than 2 meters, then we need to have isolation at both ends of that cable. So we would need to have isolation here at adjacent to the battery system, and isolation at the PCE. Now, one way of avoiding having to put in two probably identical circuit breakers is bring the PCE closer to the battery system, so it's at least 2 meters away. Now, with large systems, that can be impractical because of the size of the bank and the run of your cables. So you may need to have two. So the key thing is, if it's greater than 2 meters, you're going to need within 2 meters of the PCE and 2 meters of the battery system, a isolation device. Now, whether it's an overcurrent device depends on whether you've got a separate one. You might actually have overcurrent protection built into your battery system as well. But it needs to be isolation, and it needs to be readily accessible to the system operator. Now, that means that it can't require a tool. So this here, readily accessible, similar to a main switch. And that trips up some battery systems that have integrated integrated isolation, but you need a tool to access it. It might require an Allen key, for instance, to get to the isolator, and therefore it's not really suitable as a piece of equipment that the system operator, who may not be a licensed electrician, can access the internals of the battery to isolate it. So throw some questions at me, guys. I've got a comments window in front of me, and it's all very quiet. Let me know how it's going, if you can follow what I'm drawing. So the other thing we need to consider is cable sizing in this design, and also calculate arc flash. Now the cable sizing is based on basically how much you're going to be drawing. So you need to know what the maximum DC current this inverter is going to draw as a continuous rating for this inverter. So let's say this inverter can draw I don't know, 160 amps. So we've got 160 amps is the maximum current that it's going to draw. So our protection here and our size of our cables needs to be suitable for the load. So the cables must be able to carry the current, and the protection must protect the cables in case of a short circuit as well. So the sizing of these will be determined by both the load and the protection. So it's just the same theory as you would use in any AC design, but it's DC. Something to consider too is that running very close to the limit of a circuit breaker rating, so say we did put in 160 amp circuit breaker in here, it may well be, and depending on what the ambient temperature is, derating somewhat because of temperature, and it could false trip, so you probably want a bit of headroom above that. And the other consideration, which is a tricky one, it's known as ripple current. Now when you've got, if I do a little graph here, so this is current here, you might think a DC current looks like this. So say we've got 100 amps of current, and you might think it looks like that over time. So this is time across the bottom here. So you might think, oh well, it's 100 amps, as long as our device can carry 100 amps without tripping. But when particularly a single phase inverter is creating an AC output from a DC source, it's actually superimposing a ripple on top of that DC base current. So you've got ripple current as well, and the size of the ripple gets magnified by a bunch of factors. Basically the inductance of the DC side of the circuit, which can be just the length of the cables and the size of the cables and the spacing of the cables. So if these two cables here are far apart, you're going to end up with a larger inductor effectively. So you should be running your DC cables as close together as you can, so to reduce the loop area and therefore the inductance of those cables, and that'll help minimize this ripple current. So that's just good practice. It's not like part of a requirement of the standards, it's just good practice. But you should check with the manufacturer of the inverter. They might give you some guidance on ripple current for their product, and that needs to be factored in when you consider the value of this circuit breaker here. Okay, so all right, we've got a question here from Anne. Thanks, Anne. So the question is, hey Glenn, is the circuit breaker in the LG Chem HV 10 kilowatt hour battery considered readily accessible and therefore sufficient for the main battery isolator? You just undo a latch to get at it. Well, I don't require a tool. It might be a little bit fiddly, like you've got to lift a little safety clip with your finger and open it, and then there is a conventional no-arc circuit breaker behind that cover, and that can be operated. So I'd say yes, it can be considered readily accessible, but it's marginal in terms of whether someone would actually work out how to do it in a hurry. So I guess it's a case of a risk assessment on the system operator. I mean, after all, it is there for a purpose. If something goes horribly wrong and you need to turn off the source, you don't want them to have to be going looking for the manual and trying to work it out. So I'd probably encourage having separate isolation, but it's not mandatory. It's probably just good design. So thanks for that one, Anne. Sorry to give you a yes and no answer to that. A lot of interpretation does come down to the inspection of a system and the authorities' sort of interpretation of that standard. And it's become a bit of a problem for 5139, which is it's a brand new standard, and as a result, there's a lot of it's a bit unclear. So for things like what is the definition of a habitable room? It's not given very clearly. It just gives you a list of some examples, such as a bedroom, a lounge, a kitchen, but it doesn't give you an exclusive list, and it's kind of left up to interpretation what a habitable room might be. So there's one of the issues associated with a new standard is coming up with a generally understood interpretation of it. So we're still working through that at the moment with various regulators and coming up with a sort of industry understanding of it. Generally, with the second iteration of a standard or an amendment to it, a lot of that vagary is sorted out. I certainly remember the confusion around 5033 in 2012 when it said you had to use HD conduit when you were inside a building, but it didn't give a lot of clarity about what that meant. Whether it meant verandas or underfloors, etc. But then in 2014 it was amended and given more clarity. So that's probably something to come with 5139. Okay, so we've designed a system for I'll just cut back to it so you can see it, a system here which is a 48 volt lead acid system with 1500 amp hour sealed cells. We've put in the string overcurrent protection, so this is our string here, overcurrent protection devices, and here, and this is our main battery isolator. So just call it a battery ISO here. Now this other one is in just for the purpose of distance. If the PCE is more than 2 meters from the battery system, then that secondary one's required. Okay, so the next step we're going to do, just cut back, is to look at arc flash and incident energy. Now I talked about this earlier in the week, and I explained that you needed to consider a few things when doing arc flash calculations, and then it's a little bit complicated. The formulas are in the standard, but what I've done is produced a little calculator for you it's got all the formulas built into it. It's an Excel spreadsheet, and I've just remembered I forgot to put a link to it in the description of my earlier live stream this week, so I'll do it to this one and the earlier one as well. And I'm just going to cross over to that now so you can see it. Here we go. So that's just an Excel spreadsheet with the formulas built in. It's actually, the spreadsheet's locked, but there's no password on the lock. And the reason for locking is just so you don't accidentally bugger it up when you're playing with it. You can only change the fields that you should be changing. You can always unlock it and modify it to suit your own requirements if you so wish. So looking over here, where are we? We need to fill out these fields here. What's the battery system fault? So is it 24 volt? No, it's not. It's a 48 volt system. So I'd actually already started filling this one out before we started this event. The arcing current is actually calculated. It's the bolted fault current, this one here, divided by 2. Now, how do you come up with the bolted fault current? You need to find out from the manufacturer what this is. So I'm just going to go over to, where are we now? Over to another screen. Here we go. And this is a data sheet for a sealed lead acid 1500 amp hour battery. And oops, just bring myself up here. Got the wrong person. And there is the specification of that system. So it's 1500 amp hour. It's at the 10-hour rate at 25 degrees Celsius, and a little bit further down it says internal resistance is 0.12 milliohms per cell, and the short circuit current is 16,882 amps. So that number there is actually what we're after. That's the bolted fault current, and the definition of a bolted fault current is on the battery side of any protection that's installed by the installer. You were to replace with a 0 ohm resistor, basically a spanner, what would the current be? So yeah, short circuit right across the battery system. Now, when you've got a string of batteries, a series string of batteries, the fault current doesn't go up. The voltage goes up, and the arc flash incident energy goes up, but the fault current is the same. So it's the same current passing through all the series cells. But when you have two strings, you're doubling the bolted fault current. Now, I'll jump back to my calculator. So just remember 16,882 amps. Okay, so I'll jump back to this, and I'm just going to turn off my little thing at the bottom here. Right, so I plugged in the bolted fault current for one string, and straight away it's calculated stuff such as the arc flash incident energy and the arc flash boundary, the distance at which you need to wear PPE within, so that's 3.7 meters, and I've only done it for one string of these 1500 amp hour cells. But the reason that it's getting a red flag, that little red dot's telling me that it's a very high level of arc flash energy and the PPE requirements are quite severe. If I bring up a PPE diagram, remember 12 cal per square centimetre, and what does that look like? 12 would be category 3, so category 3, arc rated long sleeve jacket, arc rated pants, arc rated flash hood with a hard hat, safety glasses, hearing protection, leather and voltage rated gloves, leather work shoes. Gee, just kitting yourself out's going to cost a lot, let alone how easy it will be to work and all that. And hopefully you don't live in a hot place. So that's a pretty serious level of PPE for that system. But there is a solution to this, so I'm just going to jump back. The solution is we need to reduce the arcing time. This T-arc is the arcing time for, sorry, I'm clicking on the wrong thing, for this battery system when there is a bolted fault current, a bolted fault or short circuit. And the arcing time is, in the standard it says, should be listed as 2 seconds if there is no string overcurrent protection. Now, as soon as you've got a multi-string system, you're required to have string overcurrent protection. But you can even put string overcurrent protection in there anyway, even when there's only one string, just to reduce, and that would be typically a midpoint string, to reduce the arc flash incident energy. So you watch what happens when I put in string overcurrent protection. I drop down to 0.6. I get a green light. It makes a huge difference having that interstring overcurrent protection. So I'm still pretty high here in terms of the arc flash boundary, but it's really reduced my arc flash incident energy a lot. Now, the other problem is that the multiplying factor, well, you really can't do much about that. If the battery system is outdoors, open space, it's 1. If it's in a room, it's 1.5. If it's in an enclosure, it's 3. And so this battery system is in an enclosure, so it is 3. So there's not much we can do about that. The arcing time is given here as 0.1 second. You can actually calculate that from the protection device that you put as an interstring overcurrent protection device. You can look at the current time series for it and find out what the trip time is for that product, and therefore you can put it in there. So 0.1 is given as an example in the battery standard. So it really helps to reduce that. So if I plug in here, double 16.8, so it's 32, it's 33.6 roughly, so 33650 roughly. And even though that with 2 strings, I'm up to 33650, I've really significantly reduced the arc flash incident energy, but it's still got quite a high arc flash boundary. So that means you really still need to wear PPE, but the level of PPE is very, very low. So at 1.2, if I go back to my arc flash example, here we go. At 1.2, I'm really just wearing some modest protection, so an arc-rated long sleeve shirt, pants, overalls, face shield, safety glasses, hearing protection, leather gloves, and leather shoes. Starting to sound like what you'd be wearing for COVID testing, but anyway, yeah, so that helps a lot. The other consideration is, at what point are you actually working where you're exposed to this arc flash incident energy? And I'm going to try and explain this with some more drawings. I'm just looking if there's any more questions. No, you're all very quiet over there. I'm just going to bring up my diagrams. Where are we? There we go. Okay. Now, I'm going to draw this as an explanation that there are many points within a system that you need to consider the arc flash incident energy depending on who's working on it. So I'll just get rid of my diagram there. Okay. And cut over to my drawing. Right, so here I am back on the drawing pad. And I'm going to draw a string of cells. So I'll just do it as a horizontal drawing. So here we go. And dot, dot, dot. Okay, so that's a single string of cells. Let's call that a 48 volt system. So there's 24 cells in this example. Now I'm connecting onto a DC bus. So this is my DC bus here. So there's my single string. And when I look at this, there's several points that an arc could occur. An arc could occur when those cells are being loaded into the battery rack, for instance. And that would be a fault at, get a nice pen here, at this point here, at the cell level. So a cell arc flash incident. Now, there's no overcurrent protection within the cell. This is just a lead acid battery. It's got 2 terminals, and in the case of those large ones, 6 or 8 terminals sometimes. So if you put a spanner across the terminals, you will get the bolted fault current at the rated rate, at the capacity they showed. So if I go back to my spreadsheet, so I'm just imagining I'm still using the same cells in this design here. So these are the 1500 amp hour cells, and it's a 2 volt cell. So I'm going to go back to my little spreadsheet. So here I'm on the spreadsheet. I'm going to just work it out. So here at a cell level, it's 2 volts, not 48. I don't have any intercell overcurrent protection, and my bolted fault current is 16,882 amps. And it's not so bad. And it's inside a box, so it's a multiplying factor of 3. And by the way, if you wondered what D is, that's working distance. It's deemed to be arm's length, so that's where that came from. So that's not so bad at all. I'll just do the arc flash boundary calculation. So here we've got system voltage is 2. Oh, that's why I got such a strange number before. And our bolted fault current is 16,382. No, 882. Okay, so when I'm within 6 centimeters of the battery terminals, I have a arc flash incident energy of 0.5, and therefore I've entered the arc flash boundary area within 6 centimeters of the terminal, and the energy is 0.5 of a cal, which is less than 1.2 cal per square centimeter. So actually I don't need any protection. Amazing. For those of you who have actually put a spanner across a large 2 volt cell, they will know there will be an arc, but it's more of a melting and burning issue than an arc flash issue. So it's still dangerous. You can still burn yourself, and if you are wearing any metal jewelry, very serious burns can occur if they contact those cells. So it's not to say that it's perfectly safe. It's just that you're below the threshold for serious or for PPE. So it would be just basic safe work methods, protecting your hands and eyes from materials that you're working with. So that's at the 2 volt point. Let's jump back to my drawing. So over here we're now going to look at another point in the system. Now we've wired up all the cells together, And at this point, we're now going to add another string of cells. So we have 2 strings, and as a result, with having 2 strings, we're now required to have string over current protection. So I'll draw that in here. So we've got our string over current protection on those 2 strings. So let's introduce a new fault condition here. When you're installing that string over current protection, you accidentally could short circuit at this point here. So now you've got, on the battery side of the string over current protection, you have put a spanner across the terminals, and you've now got 48 volts instead of 2 volts, and you've got 16,882 amps. So I should write what the cals were. I think it was 0.5 cal here. So that was pretty low. Let's have a look what it is over here. Okay, so updating my calculator here, we've gone from 2 volts to 48 volts. And wow, there we are. We're well up, and this should be 2 seconds, sorry, because there's no string over current protection yet. So the safe working boundary is 1.4 meters, or 142 centimeters, and the arc flash incident energy is 12. So that's very, very high. 12 is when you're getting those spacesuits on. So how can we avoid having to wear a spacesuit and have that particular risk factor presented? Well, as part of your safe work method, and once again I'll cut back to my drawing, you want to avoid the possibility of that arc occurring by not completing any of the intercell connections, or at least breaking it somewhere along here. So you haven't actually, if you do not connect all of the string before you do your terminations, so you haven't connected those 2 cells together yet, while you're wiring up your string over current protection device. So this is where a risk assessment and a safe work method come in. How can you work safely in the system so you've mitigated or removed the risk of this fault occurring, and therefore your PPE requirements are significantly reduced? So here, if that fault was to occur, that's 12 cal per square centimetre. All right, so there's one more fault I'm going to draw here, and that's if the bus bar is short-circuited. So we've put our 2 strings in, we've put our interstring over current protection devices in, and we're connecting up to the main bus bar. And at this point, we go, whoops, we're pretty bad with our spanners, by the way. Just to tell a little story. Where am I? Just to tell a little story about how this can happen. One of my students who used to do a lot of UPS systems in banks and hospitals, so they were, typically 600, 700, 800 volt battery banks, so they're pretty serious battery banks, was disassembling or removing some cells with his apprentice, and they were working at either end of a string of batteries. And so they were working on just one cell at a time at either end of the string of batteries. And they were both using uninsulated tools. And the spanner, the handle of the socket wrench was hitting the wall of the room as he was working. And he just happened to realize the wall was metal when he hit it. And he looked down at the other end of the string as apprentice was doing the same thing, hitting the wall with a spanner. So they were just one coincidence away from basically having an extremely dangerous situation, possibly fatal, because of they were forming an accidental short circuit using the building as a pathway. So think about all those short circuit paths as part of your safe work method. So going back to my calculator now, here we go. So if we're doing a bus bar fault, we've now got 48 volts, yes, but we have interstring over current protection, which means we can drop our arcing time right down. So I'll drop our arcing time down to 0.1, and our bolted fault current now is no longer 16,882 amps, because we've got interstring overcurrent protection. Now, in this case, we might have put in some 250 amp fuses, so we find out what their trip time is. Sorry, I'm moving that around a bit, but let's just imagine that in 0.1 of a second they get up to 400 amps. Okay, so we've actually have a lot less current to deal with, and now we're actually very safe because of that interstring overcurrent protection. So even though we're working on the main bus bar, which might be as thick as your arm, dropping a spanner across at this point will cause the interstring overcurrent protection fuses or devices to trip and massively limit the current. So there you go. That's how you can design a system to be safe and also to work safely while you're assembling that system. I should point out, and thanks for the prompt, Laurie, this little spreadsheet is built into Solar Plus. So Solar Plus, if you haven't heard of it, is the software that my company has produced that is for designing and installing and commissioning. Basically, it does a whole lot of things. I could give a whole webinar on it later on, but not today. Solar Plus has this calculator built in for you. So as you're designing a system, you're also filling out Solar Plus, putting all the values in there, and a lot of those are already built in, such as the bolted fault current. Once you select a battery, it does it for you. So a lot of this is pretty easy when using software. So how are we going, everyone? Got any questions so far? Now, I'm just looking to see if I've covered off, or I should go back to that drawing, back to my drawing. So just to complete this, so this fault here, because we've got the interstring overcurrent protection devices, and I rated them as I arc was 400 amps on each of these. That's when your pen fails on you. There we go. 400 amps. That means that at this point here, our cal is very insignificant. It dropped to approximately naught cal per square centimetre. And that was all because we put in those interstring overcurrent protection devices here. So that's a big plus. Now, it's a requirement when you've got more than one string. If you've only got one string, it's not a requirement, but it can help with reducing the arc flash incident energy further downstream from the batteries. Okay, so that's a basic design of a. Hang on, go back to my right picture. That's a basic design of a battery system. It's a very big one. It was an off-grid system, 2 strings of 1500 amp hour cells, but we worked through the design in terms of protection, cable sizing, distance of the isolator from the battery system and from the PCE. So that's basically what I wanted to cover today, and I was sort of hoping there'd be a few more questions that I could follow up on. So I did say we'd go through a design from woe to go. We're not doing the PV side today. We're just looking at the battery side of the system. But maybe just to contrast a lead acid system with a lithium ion system, I'll bring up a lithium ion battery as a contrast, and let's go back to there. One of the things with doing stuff live is you've got to be a little bit organized. So let's see how I'm going here. Right, so this is the data sheet for Power Plus Energy's Life Series batteries. Now it's probably a little bit small. Maybe I can make it a bit bigger. Let's see if I can make it a bit bigger for you. There we go. And you'll see they have a 24, 48 and 120 volt model. So we'll look at the 48 volt model here, and we'll do a comparison with, we're choosing to use lithium ion as opposed to a lead acid sealed cell. And try and build something of similar capacity. We'll go down here, so it's 3.3 kilowatt hours per battery module. Now, how do we work out how many kilowatt hours our previous system was? So I'll just cut over to that. So I said these were 1500 amp hour cells. So that's 1500 amp hours times the cell voltage, times the string voltage, which is 48, times the number of strings, which is 2. And what do you know? I'm actually going to have to get my calculator out. I really should have done this beforehand, but here we go. Yep. Get my calculator out. It's always fun to do these things live. So 1500 times 48 times 2 equals 144,000 watt hours. And if we divide that by 1,000, it's 144 kilowatt hours. So therefore, 144 kilowatt hours total. So for those of you who are familiar with lead-acid batteries, you know that that 100% figure is not the usable capacity. And the usable capacity is based on how long you want those cells to last. A popular figure used for a good lifespan for a lead-acid battery is around 50% usable. So of that 144, if we divide it by 2, it's going to give us 72 kilowatt hours usable. There we go. So that's our usable energy. Now, with the life cells, they've got a 100% capacity of 3.3, looking at the data sheet. The maximum depth of discharge is, and I'll cut back to it so you can see that spreadsheet. The maximum depth of discharge there determines the lifespan of the battery, as does most cells really is affected by this. And so if we're going to take 100% out of those cells, we'll only get 2,700 cycles, which if you think of a daily cycled system is, I don't know, about 8 years or so. If you're taking 75% out, you're getting 5,000 cycles. So that's more like about 15 years or so. So let's say we're going to 100% depth of discharge, and we're getting 2,700 cycles. So we'll try that. That means if I wanted to build a comparable system where I'm using 100% of the lithium battery's capacity, and I need to build something that's got 72 kilowatt hours usable, I take 72 and divide it by 3.3. So I need 21.8. Let's call it 22 cells. Battery modules. So 22 battery modules. Whoa, that's a lot of battery modules, but yep, it can be done. One of the nice things about lithium-ion batteries is their modularity. You can often parallel a lot of them together to get the capacity you need. So if I cut back to my drawing over here, so instead of having 2 strings, we've actually got 22 strings. So if I'm doing an LFP battery, 22 by 3.3 kilowatt hour battery modules, I'm definitely going to have a lot of parallel battery modules. But the good news is most lithium-ion batteries come with integrated overcurrent protection. Now, don't assume that a semiconductor switch on the front of it is a protection device. It might just turn off the electronics. In the case of the Power Plus Energy batteries, they actually have built into them a circuit breaker. Cut back here, I think there's a picture of it for you. Where are we? There you go. There's a NOAC circuit breaker. This is actually their older model. This is before they put their new BMS in. So the circuit breaker looks a little bit different on the newer models, but basically the same form factor. So that circuit breaker is a string overcurrent protection device. It is readily accessible. It's on the outside. It can be locked in the off position, and it's marked on and off. So it actually meets all the requirements of 5139 as an isolation device. I'll just zoom in a bit so you can see it there. Yeah, apologies to Power Plus Energy for not showing their later models, but anyway, it's got the same functionality in this unit here. So coming back to my drawing over here, all of these are built in. In fact, they're double poled too. So we've got interstring. So that means we can bring them all onto a bus bar in parallel. Now this is where the complexity gets depends on what you use for your bus bar system. You might use your own manufactured bus bars, just bits of solid copper and drill and bolt into them, or you might use a product that's a extendable bus bar system like the Victron Links, which I'm very fond of myself, which you can just plug and play them together up to 1,000 amps of bus bar. But at the end of this is the end of the battery system, and we need to then have a main battery system isolator, or a means to isolate that whole battery system. So it could be some distance away, and therefore we've got that 2 meter consideration. So I'm just drawing, that's our main battery isolator here. And depending how far away the power conditioning equipment or inverter is, we may need another one at the PCE. So there you go. Both of these would give you a large amount of storage, but different characteristics. And I think that the comparison of lithium and lead acid is complicated, but there's a little bit of opinion and personal preference to that. I don't want to kind of go into that with my own biases, but I can say that I have seen a marked move towards lithium for off-grid systems because of lots of factors, and it even can come down to the ease of management of moving these things around, not lifting 60, 70, 80, 100 kilo lead cells around that are like massive delicate eggs that weigh a ton. Whereas with modular batteries and metal cases, they're more robust and often come in more like 30 kilo units, so they're not so difficult to move. Okay, well, I'm going to wrap this session for today, and I was, let's go back to, where are we? Here we go. Gotta bring my screen back, sorry. Okay, and yeah, thanks for turning up for my little daily live stream for what is today? Today is Wednesday, so which is it's a hump day. Tomorrow is Theory Thursday, and we're going to go and look at some basic theory around installing solar. Now, the reason I've gone back to basics for installing solar, which is probably for many of you who do it every day, you go, oh, Glenn, I know all that stuff. We've got a wider and growing audience of installers now, particularly in New Zealand as well. New Zealand's really starting to catch up with solar, and they still need to learn a lot of the basics too. So one of the things that's just happened is New Zealand's gone into stage 3 lockdown in the greater Auckland area, which is kind of pretty severe, really stopped installers working for the next 3 days at least. So I thought I'd do something really a bit focused on the New Zealand solar industry, and it's going to be about the basics of solar. So I hope to see you guys and girls turn up again at some point, maybe tomorrow, maybe Friday, and we'll do more of this live streaming. So please bring your questions and comments, and I'll do my best to answer them. So thanks everyone.